Comparison of regression loss functions. In the last few lectures, we've been looking at different regression loss functions. What is a loss function? Whenever you are training a machine learning model, you have to see what is the loss when you propagate through the model, and then you have to back propagate the loss so that you can tune the parameters and train the model. So this is the concept. When you have any input x, y, in which x is the input and y is the expected output, if you pass the input x through the model, if you are passing this, the model will produce some output y cap. We'll call this as predicted value. But this y cap won't be exactly y. Y is the expected value or the true value. So instead of this true value y, model predicted y cap, you have to see what is the difference between y and y cap. So this is the loss. But generally, you don't simply write loss is equal to y minus y cap. This is not the way, because for many mathematical purposes, when you are using this in, let's say, for gradient descent, or if you want to just calculate the loss and see what is the loss, there are many reasons by which simply this y minus y cap won't be the perfect choice. This is where you will use different loss functions which are the perfect choice according to the particular inputs that you are using. Let us say in your particular use case, you have some particular reasons. Maybe you have some sort of outliers, or maybe your noise is Laplace noise, or maybe Gaussian noise. So depending on different conditions, you may have to choose one particular loss function. In this lecture, what we are going to do is we'll see what all loss functions we have seen till this point, and then we'll compare all those loss functions and try to understand which loss function is the right choice for each of the situations. So this is what this particular lecture is for. For detailed lecture on each of the loss functions, you can refer to our previous ones. But here we are going to compare what all we have already learned. What I'll do is, first we'll simply give a basic overview of what loss functions we had gone through. The first loss function that we learned was, which was the first one that we learned? It was mean squared error. So what was the speciality in mean squared error? In this case, loss function was 1 by n sigma I is equal to 1 to n yi minus yi cap, yi minus yi cap, the whole square. What is n here? N is the total number of samples you have, and yi is the true value in ith sample. Yi cap is the predicted value in ith sample, right? So using that, we have used this formula in order to find mean squared error. So what exactly is this formula? What is the significance? How to find the gradient? Those things, please refer to the mean squared error lecture. Here we'll simply take the formulas and do a slight recap, and we'll step into the comparison part. Okay. Second one that we learned was mean absolute error. The reason I'm writing the formula is I want you to take it back in memory, whatever you learned in the mean squared error lecture. So I'm expecting that when you see the formula and the name mean squared error, automatically the other details that we discussed would come into your mind. So then the comparison between them becomes way more logical. So that is why I'm writing these formulas in the starting. Then we knew that mean squared error, this was squaring all the errors. It was making each of the error magnify much higher. So when the error is large, it would magnify it into much higher extent. In order to avoid that, we had mean absolute error. In that, we had 1 by n sigma I is equal to 1 to n, absolute value of the error, absolute value of yi minus yi cap. This is what we learned for mean absolute error. But then we had seen that there were some positives for mean squared error, some positives for mean absolute error, some negatives here, some negatives here. What did we do then? We tried to find something which can have both these positives and see if you can eliminate both these negatives. In that attempt, we had seen about root mean squared error. What is the formula here? You just put a square root on this particular mean squared error formula. That will be root of 1 by n sigma I is equal to 1 to n yi minus yi cap the whole square. So in this case, we had seen that we got some specialities of both. That is, it was able to magnify the errors. At the same time, final output was provided in the same scale as the original input. So that quality it took from mean absolute error. After this, we had seen other attempts which were trying to take the positives from both these. One was Huber loss. In case of Huber loss, what did we see? In that, we had two formulas for loss function. First one was half yi minus y cap the whole square. So in our lectures, we had used a residual instead of yi minus y cap to make it simpler. Here I am directly writing this. This was used in case mod yi minus y cap is less than or equal to delta. This delta we had discussed, it is threshold in case of Huber loss. We had to fix a particular threshold above which, below which you will use mean squared error kind of quadratic loss function, and above which what will you do? You will use delta into mod of y minus y cap minus half delta. So this is what we had used. So here I am removing I because it's not just for the ith term. That is, for each of the term you have to see which is the case. Okay. Then you have to see y less than y cap. In this case, you use this particular formula. So, okay, I'll use in this formula only. Y minus y cap greater than delta. Okay. So this is what we had used in case of Huber loss. Next thing is, after Huber loss, what did we learn? We learned about log cosec loss. In case of log cosec loss, what was the situation? Here, you were manually setting one particular threshold, and then you were seeing that whenever it is lesser than threshold, you will go for this. Whenever it is larger than threshold, you will go for this. So instead of this manual treatment, what did we do in log cosec? Here, log cosec function automatically handled the situation. So then the formula became sigma I is equal to 1 to n log cos h of yi minus yi cap, right? Yi minus yi cap. So this was the formula in case of log cosec loss. After that, we had seen one more loss function which was called as quantile loss. What was the speciality here? Instead of finding mean or median, this time you can use a regression function for any particular point, that is any quantile. Let us say you want to find 90th percentile instead of the median. That can be easily done with quantile loss. What is quantile loss function? Here again you had two formulas. We had a particular value tau. Tau was fixed as whichever percentile you want to find. If you want to find, let us say 90th percentile, then you would say tau is 0.9. So tau is somewhere between 0 and 1. This is the range of tau. You had tau into y minus y cap whenever y is greater than or equal to y cap. This is what we learned. Otherwise, in case y is less than y cap, then what will you do? Then you will say it is tau minus 1 into y minus y cap. So these are the things that we learned in the previous lectures. So I just gave a slight recap so that you will remember these things. Automatically those lectures will go through your mind. So the comparison becomes way more logical. So now we are going to start the comparison. In comparison, what we are going to do is we'll build a table. In this table, we'll fill for each of the function what are the different characteristics. Okay. So let us say for each of the loss functions, let us say you have a loss function here. Then we'll also see what is the shape of that function. I'll write shape. Then what do you want? You want outlier sensitivity. For each of the functions we had discussed about how it deals with outliers. So I'll write outlier sensitivity. After that, what else is there? You want to see whether it is differentiable everywhere. This is an important point because when you're doing gradient descent, you want to know whether this particular function stays differentiable everywhere or in some particular position it is not differentiable. So in order to see that, okay, I'll give a bit more space. Let us say shape. Then I have outlier sensitivity. Then I have smoothness. Smoothness means you have to understand it is differentiability. It basically says whether it is differentiable everywhere or not. And next one is robustness. Robustness of the robustness towards outliers. And then we'll also see what is the use case, where to use this particular function. Okay, these are the things we are going to compare. Then we'll understand which one to use under what situation. Let us say this is the table we are going to draw. In this you have the loss function, then you will have shape, you will have outlier sensitivity, you will have smoothness, robustness, and then use case. These are the things we are going to fill. Let us take the first one, mean squared error. So this is what we are going to take. Keep this particular formula in your mind. With mean squared error, what will be the shape? Shape will be quadratic because you have this quadratic term here, error is squared. So automatically your shape is going to be quadratic. So mean squared error, MSE is the loss function. For this particular function, shape is quadratic. What about the outlier sensitivity? You know, this quadratic function, it is differentiable everywhere because that y minus y cap whole square would mean even at 0 or whichever point it is differentiable. In that particular lecture, we had actually taken the gradient and understood exactly why it is differentiable everywhere. Here I will simply write, okay, we were actually talking about smoothness. Okay, I just got confused with smoothness. So I'll first put smoothness here. Smoothness is smooth. So basically because it is differentiable everywhere. So I'll just put a tick mark saying that it is smooth everywhere, differentiable everywhere. Then outlier sensitivity, what had we seen? We had seen that because of the squared term that we have here, this one, because of the squared term, if you have an outlier, that means error will be large on that term. Then what happens? If the error is large, that gets magnified. That would mean outlier sensitivity is very high. So that is what is about outlier sensitivity. So outlier sensitivity, you can say it is very high. I'll put two these things to show that it is very high. What about robustness? Because outlier sensitivity is very high, that automatically means it is not a robust model. That is, if you have any outliers, it would magnify that outlier and there won't be much robustness in the model. So I would put robustness as a dip. It's a low robust model. Next thing is, what are the use cases? In MSc lecture, we had discussed that one particular use case is whenever you have Gaussian noise. Whenever your noise is Gaussian, generally MSc is the go-to loss function. So this is one thing. Secondly, if you want to largely penalize errors, whenever you want to penalize errors largely, that is, you want to magnify errors. This is the point. You want to square the error and magnify it, then you generally go for MSc. So Gaussian noise is a big clue that you can actually use MSc in those situations. Next loss function is mean absolute error. First, let us go and check the mean absolute error formula. It says half into sigma I equal to 1 to n, 1 by n into sigma I equal to 1 to n, mode of yi minus yi cap, mode of yi minus yi cap. So what is the difference now? The difference is the squared term is gone. There is no more squaring now. This would mean two things. One is you are not going to magnify errors, and the second thing is you are going to have final error in the same scale as the actual error value. Previously you were magnifying the error. This time loss function will keep errors in the actual scale itself. So then what will be the shape of the model? Because there is no squaring, this will be linear, right? Shape will be linear. Shape will be linear. What about outlier sensitivity? This time, because you are not squaring, your outlier sensitivity will be comparatively lower. So for mean absolute error, outlier sensitivity is lower. What about smoothness? Is it smooth? Is mean absolute error smooth everywhere? So if you remember the mean absolute error lecture, that we had seen that it is smooth everywhere except at 0. So not smooth at 0, not smooth, or I'll simply put not smooth at 0. Okay, at all other points it is smooth, but at 0 it is not differentiable. What about robustness? This time, even if you have points which are outliers, still it will accommodate. So the robustness is generally high in this case. What are the use cases now? One use case is, we had already discussed that mean squared error generally goes for the mean, while mean absolute error tries to find out the median. So whenever you want your regression to be for finding the median value instead of the mean value, then generally mean absolute error is a good choice. So one point I'll write is when you want to go for median regression. Second thing is, whenever you want your regression function to be robust to outliers, whenever you want it to be robust, you generally go for mean absolute error. Then what is the next thing? Next thing that we learned was root mean squared error. Coming to formula, it is simple. You simply put a square root on the mean squared error formula. But what difference did it bring in? This time it made sure that error is already magnified because it is having a quadratic term. But at the end of the formula, after taking the sum and doing mean, then you are taking square root, which means the scale of error will come back to actual scale of the whatever input you provided. Because of this time you are having input in the original scales, and you are also making sure that it is outlier sensitive. This is the point with RMSE. Then what happens? What will be the shape of this model? Because you are having the squared term, shape will be quadratic only, right? It will be quadratic. What about outlier sensitivity? Outlier sensitivity is actually exactly same as this because you have the same square term. So outlier sensitivity will be very high. What about smoothness? See, if this is differentiable, then we had seen this is also differentiable. So we had actually taken the gradient and seen that in the lecture. So this is smooth. And what about robustness? Same reason as this. Robustness here will be low. So I'll say robustness is low. What are the use case? This is one important thing. So one point is you can use this similar to mean squared error, but the problem is advantage is this time you get error in original units. So here I'll put error. Error is provided in original units. Original units. So whenever you want error or loss to be shown in original units, then root mean squared error is a better option over mean squared error. Next loss function is Huber loss. So I'm just going through very basics. The remaining we had discussed in those lectures only. Next thing is Huber loss. What is the speciality with Huber loss? This time we tried to introduce a new factor called delta, which is a threshold. And using this threshold, we provided it the properties of mean squared error as well as mean absolute error. This is what we did with Huber loss. What did we learn in the Huber loss lecture? In this case, Huber loss. What is the shape here? So this is a bit interesting because previously you just had one function, so you can say it is quadratic or it is linear. But this time with Huber loss, you have two different formulas. And if you see, one formula is actually quadratic, other formula is linear. So you can't actually say it is quadratic or it is linear. So what I'll write is, I'll write it as quadratic plus linear, okay? Because it depends on what is the value and according to the threshold, where does it stand? It is lower than threshold or it is larger than threshold. Accordingly, it will change. So I'll put shape as quadratic plus linear. What about outlier sensitivity? You can say it is moderate because you have both sides in the same formula. So it is moderate. What about smoothness? We had seen it is differentiable. And what about robustness? This would also be medium. Next question is, where are you going to use this particular one? So if you remember from that lecture, we had already discussed whenever you want balance between MSE and MAE. When you want to balance between both two, you want both the specialities, then you go for Huber laws. After this, what we had seen? We had seen that instead of Huber laws, where you actually put one particular threshold and you made it piecewise kind of function, instead of that, what you can do is you can go for log cos h laws. What is the speciality? We had seen that log cos h function will automatically have this particular characteristic, that is, it will behave like MSE initially, and as the error increases, it will automatically start behaving like MAE. So this we had seen in lecture how it actually happens mathematically. How is cos h and log helping achieve this thing? So from that we know, in case of log cos h laws, it automatically behaves both like quadratic and linear. So here again it is quadratic plus linear, but the difference is here it is kind of artificially introduced. You introduce threshold and then you said, okay, above this threshold I'll use a different formula, then it will be linear. Before the threshold I'll use a different formula, then it will be quadratic. But in case of log cos h laws, automatically this function is behaving like quadratic function at the beginning, and once you progress, when the error is larger, automatically log cos h function will behave like linear. This is the speciality here, so keep this in mind. What about our outlier sensitivity? Let us see this. Okay, outlier sensitivity, it is moderate because you have specialities of both. Similarly, this is also moderate. Robustness is also moderate. What about smoothness? We had seen it is differentiable, so it is smooth. Next thing is, where are you going to use this? So again, you can say it is for a balance between mean squared error and mean absolute error. Another way of saying it is, you can say you want it to be a bit robust, and also you want it to be smooth optimization. So I'm saying robust because you can actually say these two are robust, because whenever the error is larger, automatically the formula is changing. So this issue of not being robust to outliers, that happens only when there is an outlier, that is when you have large error, then you are not able to accommodate it. But in these two cases, actually whenever the error is larger, automatically you are accommodating, because in case of Huber laws you will use a different formula, so it is robust. And in case of log cos h laws, again whenever error is larger, automatically log cos h behaves like linear, so you can say it is robust. Then what about the use case when you want it to be robust and you want it to be smooth? So both cases. So this smoothness is not just about differentiability. What I meant here is, when I say smooth, this function is smooth when compared to what you use for Huber laws. In case of Huber laws, you specifically introduced a threshold, and then from that threshold you just jump to a different function altogether. But in case of log cos h, you are not jumping onto a different function. It is the same function itself. So there is the same function that can be behaving in both ways. Okay, so that is it with log cos h laws. Then finally we also learned about quantile laws. What is the speciality of quantile laws? We had seen that till this point, all the loss functions that we discussed, all of these were either finding mean or median. But what if you want to find out some particular percentile? Let us say you want to find 90th percentile. What will you do? In these cases, you want to find some particular percentile or quantile, then you go for quantile loss. What did we learn about quantile? First, you have to fix one particular value tau, which will be in the range 0 to 1. So this will say what quantile you want to find. If you want to find, let us say 90th percentile, you would say tau is equal to 0.9. If you want to find, let us say 20th percentile, you would say tau is equal to 0.2. This we had learnt in quantile loss lecture. So accordingly, you had two formulas depending on what is your value, that is whether y is greater than y cap or y is less than y cap. Y is the true value, y cap is the predicted value. Again, because you are having two values here, see one thing, previously whenever you had two formulas here, the reason you had two formulas was in order to make sure that whenever error is larger, you will have mean absolute error kind of behavior, and when error is smaller, you will have mean squared error kind of behavior. That is quadratic behavior initially and linear behavior as you go ahead. But in case of quantile loss, you are having two formulas because this will make sure that whenever your, let us say, tau is somewhere like 0.9, then for all the errors which are lower, that is underestimation, you will have one particular behavior, and for overestimation, whenever you are having more value, for that you will have a different loss function, different behavior. That is why here it is based on whether y is greater than or equal to y cap or y is less than y cap. So that is why in quantile loss we are having y greater than or equal to y cap check, but in Huber loss we are having check with respect to the threshold, right? So in quantile loss, what can you say about the shape? So this is a kind of asymmetric linear shape. So I'll put asymmetric linear. And then what about outlier sensitivity? Coming to quantile loss, you can say outlier sensitivity is low here because like MAE, you are having linear term. You are not having a quadratic term which would magnify outliers. So you can say outlier sensitivity is low. Here it is, I'll mark as low. What about smoothness? Again, because you are having this linear term, when you differentiate, at 0 it won't be differentiable. So I'll put not differentiable at 0. At all other places it is differentiable. Next thing is robustness. What about robustness? Because it is not sensitive to outliers, robustness will be high, right? Robustness will be high. What is the use case here? Here the use case is different from all other things we have discussed. Here it is when you want to find some particular quantile. So when you want your answer to be some particular quantile, let us say you want quantile forecasting. Quantile forecasting, I don't have space, I'll write here. If you want to do quantile forecasting, so instead of mean or median, if you want to find some particular quantile, this is the use case for using quantile loss. So it is slightly different from the use case of all other loss functions. So these are the loss functions and the comparison. We learned about mean squared error, mean absolute error, root mean squared error, Huber loss, log Cosec loss, and quantile loss. So these are the regression loss functions, main regression loss functions you should be aware of. So majorly these three are what you should be aware of. I just gave you three more, which are the next few important ones. From the next lecture, we'll move from regression loss functions to classification loss functions. So this is the last lecture on regression loss functions, comparison of all the regression loss functions.